All right, great. So hey everyone, let's get started with class. All right, so I know everyone's excited about the homeworks and the projects, but it'll be more effective if you, I think if you listen to me. So try and contain your excitement for a little bit. So let me first start by answering a couple of questions that have come up with the homework. Let's see. So first of all, I've seen some good use of the discussion forums. This is great. Please continue to do that. It's better to ask questions on the discussion forum. I think on average you'll probably get a fast response time, and you'll probably often get a better response than if you email just one person. So there are a couple of things that came up. So one is the runtime for the kind of the extent of the experiments for questions 1 and 2, where you need to scale them up. And some people, and it was in the forum, their discussion, it should take at least minutes. It sounds like that if you implement it with in a high-level language with using data structures well, it might only take a few seconds, and so doing that should be fine. So don't get too disturbed by that. The other thing is you'll need what's called a cumulative a cumulative density plot. And so this should look, so you're going to get a curve that's going to look something like this, okay? And kind of judging by how you calculate the curve, we should kind of be able to tell if you've done the assignment correctly, based on various properties of it. I'm not going to tell you all of them, but so it looks something kind of like this, where this is the value k, which is had to do with the number of trials needed for this, and this is going to be the probability that it took k or fewer trials. Okay, so if you have, if this is the value right here of this is say 100, then this is the probability. So this goes from 0 down here to 1 up here. If this is 0.4, then it said 40% of the trials took 100 or fewer. 400 of the 40% of the experiments took 100 or fewer trials. Right. So your plot should look like this. Okay. So that's cumulative density plot. Yeah. Question? Yeah, you can plot this however you want. Yeah, so go wild. There was some discussion on the forum about this. You know, do it any way you want. What I want you to get out of it is to do the experiments to kind of actually believe these actual weird things with these random phenomena, and to kind of get a little bit accustomed to using these randomized algorithms. So the next assignment, you're going to need to use randomized algorithms, some of the similar parts of it, to do some more complex data analysis. So this assignment is kind of a warm-up to get you thinking about randomness a little bit, and to kind of do some problem solving and thinking about data structures. If you don't implement things well, you don't use data structures in the right way, these large-scale versions of the problems can take a really long time to run. And I've had people in the past who just couldn't scale them up that high because they weren't thinking properly. And I kind of want you to prepare you, if you aren't sure how to do the data structures here, you're gonna kind of, you don't think of it as using the right data structure underneath, problems later on are also going to be hard. So kind of start thinking about it in this way. And these problems are kind of more specific and abstract, and the other ones will have to do with some other sorts of data. Great. Yeah?
So for the k-axis, can we just focus on the experimental data, or you have to have the full spectrum. So
yeah, so only on the experimental data. Yeah, so I want to see the part where it has data. I don't need it, to go off. You can have it go off here, and what's going to happen is it's going to hit 1, and it's going to stay empirically at 1, and that's not interesting. Yeah. So show me the part that's interesting. Yeah. The questions. Okay, so the homework is due on Wednesday. The turn-in is through Canvas, and I expect you to generate one PDF document and upload it through there. You don't need to include code. You don't need to write up tables of the data. I should be able to figure out what you're doing by looking at the various plots you make, or the TAs should be able to. And then on Monday, the project proposals are due. So a lot of you have been talking to me about that. That's great. If you're looking for partners, look for people after class or before class on Wednesday, and use the discussion forums. A lot of people are doing that. That's great. And feel free to email me with basic ideas or come talk to me quickly, and I can give you some feedback. But also, that's part of what the proposal is to do. If you don't have a really great project in the proposal, I'm not going to, as long as it fulfills what you're supposed to do for that, I'm not going to dock you points for that. I can give you more feedback then, but it's often easier to do it in person before you do that, and then that's just going to be kind of a check mark that you've done it. Great. All right. So any questions about that either? Okay. Cool. So. All right, so we're going to start by kind of skipping backwards first, and we're going to talk about something that it's in the notes under lecture 3, and I didn't spend any time on this because I don't think it needs a full, should be R in here, so it doesn't need a full lecture, but this is something that we'll need for the lecture today. So I want to talk about the on these Chernoff huffing bounds, and this is related to the bonus question as well. So this is a really important thing, and you may not need this for class for any particular thing we do, but I think it will really help your understanding of what's really going on in the underlying thing, and you won't need it beyond the bonus questions. Okay, so the idea is that when we talk about, what is data, it's when you're getting these data points, and these are coming from, these are all drawn from some underlying distribution, and these are drawing IID, so they're all drawn. It turns out you can do this bound without them being totally IID, but let's assume they are. Okay, so now if you want to somehow analyze this, and you want to somehow estimate some parameter which describes the distribution, and so let's say that this is interesting when we want this to be the expected value of xi. Okay, so we want. So we want that the expected value of each of these random variables xi is equal to this parameter that we want to estimate. So sometimes it's equal to like twice the parameter you want to estimate, but that's good enough because then you can divide it by 2, something like that, right? But so you want to estimate some parameter, and if these random variables have the right expected value, okay, so you want this property, you have the right expected value, and 2, you have that there's some range where xi falls between a and b, right? So you have some, it's a one-dimensional variable. There's some a and b, and there's some probability distribution of where this variable falls, but it's 0 if it's less than a or greater than b. Okay, and so we're going to write. And what we need is this range delta, which is b minus a. Okay? And so now we can use this to, and there are various ways of writing this. So we can use this value, we can calculate this value m, and let's say this is 1 over n, and I think I have it in the notes written a little bit differently, xi. So this is the expected value this is like the expected value you would estimate from the data. And so you have also that the expected value of m is equal to theta. That follows from this property here by linearity of expectation. Okay. So now you want to say, how good is this estimate m, right? All we knew about each of the xi's was that it had the right expected value and it had some bounded range. It couldn't be anything, right? If these were Gaussian random variables, they could be anything. There's no bound on where they are here. But if we have this bound, then we can say the probability that let's write this differently. Well, okay, the expected value of m minus the true value of m. And remember, this expected value is what we wanted to estimate. So this was theta minus what we did estimate. Say probably that this was greater than some value alpha, which we can choose. Then this will be less than 2 times the exponent. So this is e to the power minus 2 alpha squared. This is n. by delta squared. Okay. All right, so I say the probability that the error is greater than some value that we can set depends on this alpha value, the number of trials we've done, and this range. Okay, and so this fits into here, and then typically what you do is you set this less than some parameter delta. You say the probability I'm outside this range is less than this probability. And then you can solve for how many samples you need based on alpha and delta, this big delta, in order to get this error bound. So another way to do this is to look at a picture. So you want to estimate, so this is this theta, and you get a distribution of where your true value m, right? So this is the value theta, and this distribution is you're getting a probability distribution over the value m. And so you may have had something like that B was out here and A was out here, and they're probably much further out. But the more samples you get, the narrower this distribution gets. And what you want to look at is for some value, some range, and this distance is alpha. So you want to say that my estimate is within alpha of the true value theta, right? So I want to say it's in here. I want to only look at this part of the distribution, and I want the integral here to be at least 1 minus delta. So if I said delta to be like 1%, then 99% of the time I'm in between these minus alpha and plus alpha from the true estimate. Okay. So this is what this Chernoff bound is telling you. It's saying, and it's doing this really cool thing. It's saying we can take these really simple estimates that just have the right expected value and are bounded in some way, and by putting a bunch of them together, we can squeeze this range to be really small. We can make this alpha arbitrarily small, this distance, how far I am away, and I can say with really high probability, I'm going to be really close to the true answer, even though I'm only getting these very simple estimates.
M is the expected value of x, right?
M is also the expected value of x, because this is the empirical mean, right? And each of the x's has the expected value of theta, which we want to estimate, right? Yeah. So it's going to have the right expected value, and the question is, if you put a bunch of these together, how far away can you be? And so this kind of principle where you're going to combine these simple estimates into create one much better one is going to come up over in class. And the first time we'll really see this is going to be in what we do today. Okay. All right. So let's leave it here. It's the Chernoff-Huffing bounds. And we'll come back and see this a little bit later in class, how to use this. Okay, and there's a bonus question. You can kind of experiment with this. There's also something that is in the notes that I won't talk about here. That's called the union bound. And this is true for this estimating this one quantity theta. But if you want to estimate many quantities all with the same data, then you need to kind of combine together these estimates. And the union bound tells you how to do that. And so part of the bonus question, you need to use the union bound as well. Okay, so what we're going to talk about today is what's called Minhashing. And so what this is doing is, last time we had shown that how to take some document. Okay, and there are several ways that we could represent the document. One was this bag of words, which I just mentioned briefly, and this transformed the document into some vector. Okay, and then vectors, you can take the distance between vectors. It's kind of fairly straightforward. You can use the Euclidean distance or other distances, and we'll talk more about how to deal with vectors efficiently in various ways in the next lecture. But what we spent more time on, and what is often used to get, sometimes has a bit more kind of contextual information of the data, is this structure based on these n-grams. And this turned the document into this set. Okay, and so now we want to say, take two documents. So we want to say, what is the similarity? So in fact, we want to say, what is the Jacquard similarity between so these two documents, so document 1 and document 2. Now these are both sets, and we defined the JS. Let's say I'll use A and B here. Again, was the size of the intersection of A and B divided by the size of the union of A and B. And so this is a similarity. It's going to be closer to 1 if the the sets are more similar, and it's going to be closer to 0 if they're less similar. But we didn't talk about how to quickly calculate this. And so on Wednesday, we're going to talk about, we want to find all of the similar documents. Say we have a huge set of documents. We want to find all the sets of documents which are similar to each other. So think of this as you all turn in homework assignments, and I want to find all these pairs of homework assignments which are too close to each other, which maybe means that people were copying. So I want to do that, all of them, and maybe in this class I have 100 or so of those, but if you're doing one of these, a much bigger class, even 100, checking 100 pairs is going to be something like 5,000 different pairs I need to look at. I don't want to calculate all these similarities. All right, so that's with 100 documents. So I want to somehow do that quickly, and doing that with just sets is going to be really tricky to do. Even calculating the distance between sets is kind of going to be a painful process. So what we're going to do is we're going to turn these sets, we're going to go today from sets to a form of vectors where if this is the Jacquard similarity, then this will use something that looks like the Hamming similarity. The Hamming similarity you can define on vectors, and I'll show as well, which is basically just showing the fraction of spots in the vectors where they have the same value. Okay, and this will be much easier to work with, and the vectors will have a bounded length that won't depend on the size of the set. So these sets can be really big. The size of the vectors is going to be bounded in size. I can make the sets as big as they want, right? So even if you turn in homework assignments or code that's a really long piece of code, the vectors may be of length maybe 1,000 bits. And I can just look at those 1,000 bits and see how similar this long, these 10,000 lines of code kind of assignments you've turned in are. Okay, so and we'll use a technique on this called Minhashing. And in order to do this, we're actually going to take a detour. We're going to go from sets into a representation as a matrix, and then from the matrix into a vector. And so this part is going to be deterministic. This one is going to be random. Okay, so we're going to deterministically map them to a matrix and then into vectors. And you don't actually need to go through the matrix. This is just will be to help you explain how this actually works. All right. Okay, so let's first go from this way of turning a set into a matrix. And so this is going to seem kind of like it's a stupid thing to do. Okay, and it's going to seem kind of silly, but then we're going to show how you don't actually have to do the parts which are silly. Okay, so let's go through an example here where set 1 is going to be 1, 2, and 5. Set 2 is going to just have the value 3. Set 3 will just have the value. We'll have the values 2, 3, 4, and 6. And set 4 is going to be 1, 4, and 6. Okay. All right. So the way you're going to represent this as a matrix is you're going to think of having a column that has all of the elements in it. Say 1, 2, 3, 4, 5, and 6. And then for each of the sets is going to be a column. Okay, and then I'm just going to record, I'll record in each cell a 1 if this appears in the set, right? So 1 is in set 1, 2 is in set 1, 3 is not, so I do a 0. 4 is not, a 0, 1, 0. Set 3 is mainly zeros, except for set 2, sorry, set 3. And right, okay, so here's how we've turned these sets into this representation as this matrix. And so remember that when we did these n-gram constructions, these sets are going to be, there are going to be a huge number of things that can be in here. If it's a 2-gram for words, and say there are 10,000 possible words, then the set could potentially, the elements could potentially have 10,000 squared possible elements I would see. And I don't want to record all those in a matrix. They're almost all going to be, it's going to be almost all zeros. Okay, so there are ways to represent a matrix using the sparse properties so you don't actually need to store all the zeros. And so that's going to be similar here. But we aren't going to need to store all the zeros. But in the meantime, it'll be useful to think about all the zeros. Okay, and so you can think of this as a matrix. Again, columns are the sets, rows are the elements. So who's heard the term sparsity before, or a sparse matrix? So yeah, so you guys, who's not heard this before, right? Okay, so most people have, this is the idea where a lot of data there's especially with you have this buzzword, this you have this big data, right? It's often, it used to be you had these databases where you had a bunch of this tabular database where you have a fixed set of columns of attributes, and for every row in the database, you had every element in the column. Now this is much less so. You're collecting data in various different ways, and you don't always fill it in. And this is just an instance where you have lots of zeros. So way to think of it is, as the number of rows and columns grows, the number of non-zeros may grow linear to the number of rows plus the number of columns, not number of rows times the number of columns. Or maybe with some log factors or something. But it's almost all zeros, especially as the data gets larger. Okay, so how do we take this matrix and do min-hashing? Okay, so this is the deterministic step. The random step, we're going to go this, and we're going to do a random permutation. So I'm going to randomly permute the rows. Okay, let me just, Okay, so I'm going to randomly permute these rows here. And so by doing that, instead of just, so, I ordered these elements 1, 2, 3, 4, 5, 6, but these didn't mean anything. They're just labels. So let me randomly reorder these. 2, 5, 6, 1, 4, 3. And so then for the same sets, I haven't really changed as long as I know the labels, I haven't really changed the information in these matrices. So now I'm going to have 1, so this is, again, the set 1, set 2, set 3, set 4. So 1, 1, 0, 1, 0, 0. Set 2 is going to be 0, 0, 0, 0, 1. Set 3 is 1, 0, 1. And set 4. Okay, so I haven't really changed the information. I've just randomly permuted these columns. So this is kind of conceptual step 1. Then for step 2, I'm gonna kind of turn this matrix for each set into a single number. Okay, so I'm going to go to a single number. We're going to say m, and this will be some map. M of S1 is going to get the value 2. Okay, so what this is going to be is, how do I get this value 2? This is going to be the first row where I have a 1. Okay, so this is first row with 1. Okay, so that was the value for S1. For MS2, this goes all the way down to the value. And so I'll write the label of the row, but you can do, turns out if you just take the number, the ordering, you could put this as a 1, 2, 3, 4, 5, 6. But I'll use the actual label here. So S3 equals, is also value 2, and M of S4 is going to be 6. Okay, so I've turned these sets into a single number. Okay, so now it turns out that this single number that I've turned the sets into is sufficient to estimate the Jacquard similarity. So now finally step 3 is that the Jacquard similarity between S1, S2 is going to be this is our estimate of the Jacquard similarity, so I'll put a hat on it. Usually put a hat on something if it's estimating it. Is going to be 1 if m of S1 equals m of S2. And it's going to be 0 otherwise. Okay, so it's a pretty stupid estimate, right? It's either 1 or 0. Now the Jacquard similarity, 0 might be possible. You're probably going to get some Jacquard similarities of 0, but you're probably not going to get 1. And in these cases, the Jacquard similarity, I guess, between S1 and S2 is always going to be 0. But for S2 and S3, you would do it the same way, and it's going to be this is going to be 1/4, right? Because the intersection is just the object 3, and the union is everything in S3 here, right? And the intersection between S3 and S4 is going to be size 2 over a domain of size 5, so it's going to be 2/5. But my estimate can only be 1 or 0, so it's a pretty kind of stupid estimate. But it's going to turn out that this is going to be kind of the only thing that we need in order to kind of get a much better estimate. Okay, so and we can do that through applying the Chernoff-Haupting bound to get a much better estimate out of this by kind of doing these random permutations and then using these single numbers to estimate the Jacquard similarity. Okay, so and this whole thing seems very, very inefficient as well, right? Computing this matrix, permuting it, then finding the top thing seems like it's a lot of work to do this. So it turns out you can actually do this very efficiently as well. So the rest of the lecture will do two things. I'll show you why this approximates the Jacquard similarity well, and how to kind of use this as a tool, and then how to compute this vector efficiently. Okay, so you're going to show that this actually works to compute it, and you can compute this vector efficiently, and then you have these nice representations of these sets, which represent the documents, which you can then use to compare documents very efficiently. Well, we don't know how to compare them efficiently yet. We'll need to talk about that with locality-sensitive hashing, which will be the topic of the lecture on Wednesday. Okay, so any questions so far about how the process works? So how would you calculate a random permutation of a matrix? How would you do that?
Random number generator?
Okay, yeah, but how? How would you use a random number generator? Yeah.
There's an algorithm that I can't remember now that you can use to map you can basically index permutations and you could just iterate through it just continuously taking numbers.
Yes. So, I mean, there's this, if you really wanted to do this, there's this classic algorithm by Knuth. Don Knuth is this, so hopefully everyone's heard of Don Knuth. He's a famous computer scientist who's at Stanford, but he wrote computer science textbooks in the 1960s before computers existed, or was working on it back then. And so he has this algorithm for efficiently permuting sets. And basically, you just go through, and every time you see a number, you have a chance to swap it with something random that occurred before it. You swap it with something random, then you go to the next one, swap it randomly. And this creates a random permutation. So that's one way to do it. Turns out there's going to be an even faster way to get this, because we don't actually need the full permutation. We're just going to need the top number. And so we're going to be able to get just this top number more efficiently than doing the permutation. So think of another simple way is like if you're sorting, you can do something like the selection sort. Well, yep.
Just confirming, is this in essence equivalent to choosing a word and like randomly out of all possible words and then checking whether it exists in every document?
Yeah, so
because that's essentially what seems to be what's happening here.
it's similar. We'll see next that there's something nice about the Jacquard similarity that you're kind of like picking. It's going to be kind of like when you're comparing two sets. You can be kind of like picking a random word from one of the two sets and seeing if it's in the other. That's kind of what you're doing here.
Yeah, exactly. One of the
Yeah, but it's working it's doing it in a way that's oblivious to what words are actually in those two sets. You don't need to know those words ahead of time. And it's going to work for all the sets you do it at once. So you're going to create a single representation which will work for all of the sets, not just two sets. Okay, yeah. All right, so let's see why this works. So we're going to show that the expected value of Jacquard similarity hat, and I'll leave off the notation where I write which two sets it's of. It's going to be between two sets, say 1 and 2. So actually, it'll be more clear if I write that. So we're going to say that the expected value of the Jacquard similarity hat between 1 and S2 is going to exactly equal the Jacquard similarity between S1 and S2. So we're going to get the right expected value. Okay, so this is a good start. It's not going to tell us, how to get a very accurate thing, but we're going to say the expected value is right. Because the 0 or 1 is not very useful, but the expected value is a good place to start. Okay, so the way to see this is that there are 3 types of rows that you're going to have in any two sets. Okay, so we'll say type X is going to be, and let's just look at this with two sets, but it doesn't matter which two sets we're actually comparing, right? So type X is going to have a 1 in both columns. So this means that row corresponds to elements from both sets. Type Y equals a 1 in one column and a 0 in the other, and the type Z, sorry, it should be type Z is going to be a 0 in both. Okay, so most of the columns are going to be these type Z columns because these matrices are going to be very, very sparse. Most of them are going to be empty, right? So the type Z columns are going to be, it's going to be mainly type Z columns. So let's say that the number of these, so the number, this is a value X, this is Y, and Z, and so so then the number of rows is going to be equal to X plus Y plus Z, right? Okay, so I claim first that just using these values X, Y, and Z, I can write down the Jacquard similarity between the two sets. Right, so in terms of these values X, Y, and Z, how can I write down the Jacquard similarity?
X over X, Y plus that. X plus Z, Y.
Yeah, so it's the Jacquard similarity is going to equal X over X plus Y. Right, that's exactly the Jacquard similarity. It's the intersection, that's a 1 in both columns, over the union, which is a 1 in one of the columns and 0 in the other, or a 1 in both columns. Right? So the union is not just the sum of the size of two sets because it doesn't count these twice. Right? So it's exactly X over X plus Y. Okay, so now I just need to show that the expected value of this is equal to X over X plus Y. And what's cool about this is it does not depend on Z. There's no Z in here. It does not depend on this value, which is most of them are these type Z values. It only depends on these values X and Y. So it only depends on the objects that are in one of the two sets. Some of the other similarities in the notes don't have this property. So this makes the Jacquard similarity nice. It's one of the things that makes it nice. Yeah?
So because Z is part of the universal set, right?
Right. So if I want to say the universal set, that's X plus Y plus Z. And I don't need anything that's in Z. That doesn't affect my Jacquard similarity. Right, so this becomes a really nice property. Okay, so now I need to say that so what I say is that So I want to say that the probability that M of S1 equals M of S2, I want this to be x over x plus y. So this is what I need to show. If I show that this is true, this is the probability that I get a 1. So I get so now my expected value of, if this is a value p, right, then this is going to be equal to 1 times p plus 0 times 1 minus p. And so so this part is meaningless, and so this gets my expected value. So if I show that the probability of them intersecting is exactly x plus x over x plus y, then I'm getting the right expected value. Okay, and so should not be so hard to see. The only thing that can be the top element in one of the two sets, right? So let's look at if I look over, so because this formulation does not depend on the T0 and on this type Z, I can ignore all of those rows. It doesn't matter where any of those rows are hashed, right? So if I just look at these rows here, and I see which one of these rows is on top, which is on top. So there are two options. So either option A is type X on top, and option B is type Y on top. So that means it comes earlier in the permutation. So if it's type Y on top, that means that one of the two rows has a value of M that is different from, is going to be a row where the other one has a 0. So that means the other set must have something. It's going to come later. It's either be type Y or type X. It doesn't matter. It's going to be a different value of M. If it's type X is on top, they're going to have the same value, right? And so this occurs, X out of X plus Y, and this occurs Y out of X plus Y, right? And so this is exactly the probability that they intersect is this type A case, and it occurs with probability X equal over X plus Y, which is what we wanted. Right, so we've proven that this is a QED, whatever. We've proven that it has the right expected value. Right, so by doing this simple thing, this random permutation, we can get the right expected value. Okay, cool. So now we have this right expected value. How are we going to get a better estimate? I want to say that. I want to say something now that the probability of something, let's call this sub k of S1, S2. I will say the probability that this is minus the true Jacquard similarity of S1, S2. I want to say the probability it's less than epsilon, some error, is going to be greater than 1 minus delta. And right, so let's put actual numbers to these things. So let's say this epsilon is going to be something like 0, 1. So if I get like a 1% error here, and I say the probability that so I want this whole value here to be something like 99%. So that means this delta is going to be also 0.01. Okay, so I want to say that this estimate here, now this is going to be slightly different than what I had before, that single number. That was 0 or 1. I want to get a better estimate that's very close to here. it's going to be less than 1% off 99% of the time. Okay, so how would I get a better estimate?
Try a couple times.
Yeah, so try a couple times and take the average. Great, yeah, that's it. Right, so what I'm going to do is I'm going to get these values, I'm going to get these hash, these essentially these special types of mapping functions, M1, M2, up to MK. And each of these is going to be, so this MI is going to be from, it's going to say take my input set and it's going to map it to some element be in something in this, one of these elements in my domain. It's probably not the right notation, but right. So what it's going to do is it's going to take my set and it's going to turn it into a number, and I'm going to do this for each of the sets, right? So I'm going to say that I'm going to have M1 of S1, M2 of S1, M3 of S1, up to MK of S1. And so this is going to be a vector of these numbers. And I'll do the same thing with M1 of S2, M2 of S2, up to MK of S2. Okay, so I'm going to get these vectors of length K. And so K is going to be this parameter up here. And that's the number K I need is going to be, the more K, this is going to be a more accurate estimate. Okay, and so, and then I'll estimate this value between S1 and S2 is going to be the average over how well each of these maps work. Each of these will be constructed by taking the matrix, randomly permuting the matrix, and taking the top element in each of the columns. Right, the same way we described before. It's going to be 1 over K times the sum over, so it's going to be this, what's called an indicator function, where it's 1 if the quantity is true. All right, so it's going to be 1 if these are equal, and then 0 if they're not equal. So I'm essentially adding up the number of times that they're equal and dividing by K. So I'm taking the average of all these. I'm doing K trials, and I'm taking the average of these. And so this is going to be a better estimator. Okay, and so what's going to happen is we started, so if we go back, think of, so now we're going to be able to apply this Chernoff bound. What's going to happen is that I knew it was between my estimate, each of the estimates I can think of as each of this value here, this is some random variable xi, and I knew it was between 0 and 1. In fact, it was either 1 or it was 0. So it's as bad as it could be. It was either one side or the other. It was never in the middle. But I knew it had the right expected value right here. Right? So maybe this was the true Jacquard similarity. And I'm going to combine a bunch of these things together, and I'm going to get a distribution of my estimate is going to be right around the true Jacquard similarity. And I want to say that the distance from here is not too far from the truth. So it's going to be, pretty close to what it's supposed to be if I use enough of these estimates. And I have the two properties I need, right? I needed one thing, that the expected value was right? So in order to apply the Chernoff-Hopting bounds, I need two things. One is that the expected value of my estimator, of the Jacquard estimator, is my true thing I want to estimate. In this case, that parameter turned out to be the actual Jacquard similarity. And the other thing is that each of these random variables, so these xi's are, it's less than or equal to 0, and less than or equal to 1. So that means that my delta parameter is equal to 1. Okay, so this delta is equal to 1. It has the right expected value. Okay. So let's see. So we have time to go through and can plug this into the Chernoff-Hopting bound. I'll just go and do this quickly, show you how this works. People interested to see that? All right. Okay, so we're going to have these random variables, x1, x2, up to xk. And we're going to have that the expected value of each xi is equal to the Jacquard similarity, and that this delta associated with it is equal to 1. And so I'm going to say that and m equals 1 over k sum of these xi. And then remember, these xi and each xi is equal to 1 if MIS equals MIS2 and 0 otherwise. Okay, so now I can say that the probability that let's see, so what I want to bound is the probability that the Jacquard similarity approximation minus the true Jacquard similarity, I want to say was greater than the probability it was less than epsilon is high, and so I'm going to say that the probability it's greater than epsilon is low. Okay, so this is going to be equal to the probability that my value m, right? M is this empirical estimate, right? Minus the expected value of m is greater than epsilon, right? So I just mapped the true Jacquard similarity is equal to my expected value, and this is my m here. So now we can apply this bound. This is going to be less than 2 times x exponential of, let's see, minus, it was 2, and now the alpha was an epsilon squared, and now I have a k up here, divided by delta squared, which was 1. Okay, I want to say that this is less than or equal to delta. Before I said, if you look back at this, I want to say the probability it was less than epsilon is greater than 1 minus delta. So the probability that it's less than epsilon is going to be less than delta. Did I say that right? Here on the other page I have the probability it's greater than epsilon is small, means the probability it's less than epsilon is large, right? Okay, so.
Why did you change the operation?
Well, because if you go back to the Chernoff-Hopting bound, it's usually written this way. The probability it's greater, it's outside some error bound, is going to be small. And the reason you typically write it that way is because this makes it easier to apply the union bound, which often comes with it, but we're not going to need to go through that here. It turns out in order to ensure multiple things are going on at once, basically you say this delta becomes the delta divided by L, where L is the number of things that you want to go on at once. And if it's 1 minus delta, it's I don't know, it's just a little, it's not that hard to do, but it's a little trickier. And so it's usually written in this form. So I've translated it into the form of the Chernoff-Hopting bound at this point. And now I'm in this form, and so I say, in order for this to be true, I need k to satisfy this property for some value delta, which is, say, 1%, and some epsilon, which is 1%. So I say k. So if I solve for this, let's go do this in a couple steps, because it's usually confusing the first time you do it. So what you need to do, so let's do exponent of minus 2 epsilon squared k. the 1 I can drop, is less than or equal to delta over 2. So now I can take the natural log of both sides. I get negative 2 of, of natural log of delta over 2. And I want to get rid of this negative, you do this. Okay, if you take the negative of a log, it flips the argument of it. And now it's easy to solve for k. I say if k is greater than 1 over 2 epsilon squared times the natural log of 2 over delta, then this will hold. Then my property holds. So I've solved for k. If k is large enough, then this property will hold. That means my error will be small. Okay, and so let's plug in some values here just to see roughly how bad this is going to be. You know, this is not a great bound. It works a little bit better in practice than this. But if I wanted 1% error, this need to be 1 over epsilon would have been 100. So I'm squaring that. I'm getting 10,000 divided by 2. So I'm getting 5,000 here because I'm dividing by 2 times log of 2 over 1 over 100. So natural log of 200. Natural log of 200 is, what is that going to be, like 6? Is that about right? 5 maybe? Let's say 6, I'm estimating here. So then I'm going to need 30,000 elements. Okay, so it seems like I've turned an arbitrary set, and it didn't matter how big the set was, into a vector of size 30,000 with these properties. You can often get away with something much smaller than this. Maybe 1,000 is going to work pretty well. And there are ways to get slightly better bounds than this, but this is kind of a rough approximation of how it works. And there's a couple of other things you can do. Instead of taking these k independent things, you take one hash function, and so you get, if you go back here, you've permuted this set here. Instead of doing this whole operation k different times, you can take the top k things that occurs inside of this, inside of here. That yellow doesn't show up at all. Okay, so I could take the top 2 elements in here. In this case, there's only 1 element, but I can take the top 2 elements instead of the top 1 element, and do that for any k, and then you can combine these together, and this is called like a where this was a min hash, this would be called a top k hash or bottom k hash, and this works a little bit better too. So these, you can get a bound, and this was just to show you can get a bound. 30,000 is not, necessarily useful, but around 1,000, this really starts to work pretty well. And this was 1% error of getting 1% off. In practice, if you did 5% off, which might be good enough because you've already approximated this distance, this is going to come down a lot. This is going to be, instead of 5% would be 20, so that would be 400 divided by 2. That's 200 times 6. So yeah. Okay. Yeah.
So the type Z situations, like those are going to depend on your data. Like, do we have any bound in how frequently those occur?
Well, so those will never influence this M function, this mapping function, because you're looking for the first object in any set, and that one will never be in one of the sets you're actually computing. Right, so you aren't going to have to worry about you're going to have to worry about the type Z objects, because those aren't going to those will not go into your summary. Yeah.
So basically, to sum it up, we're basically identifying roughly how many items we need in this set in order to achieve our type balance.
Right. Yeah.
Whatever percentage we want.
Right. And you can tune these. If you change the value epsilon delta, you'll get a different number you get here. But this is kind of a guarantee, and sometimes it'll work better than this.
Under what conditions would your epsilon be different than your delta?
Just say I wanted a really small probability of failure. So the delta is the probability of this failing. So I said I want to make that 1 out of 1,000,000. And that's not going to affect it as much. I go from log of 200 to log of 2 million. It's going to affect this factor 6, but not as much as if I change this epsilon. Maybe I only care about 1%. As you'll see, you actually do this in the homework. You'll see that 1% is a pretty small margin. The things that are really similar are going to be a lot, are going to be, something similar might be like 0.25 or something, and something far might be close to like 0.01 is the Jacquard similarity. So if you're off by 5%, you're still probably going to capture those.
So K controls the number of different M functions that I have?
Correct, yeah.
So M is basically a hashing function now?
Yes, right.
I mean, how do I choose M in real life?
Yeah, okay, so let's talk about that next. That's the next thing I was going to talk about. Great, yeah, so this process seemed very inefficient. We're going through this matrix, we're randomly permuting it. There's a way to kind of skip the whole matrix formulation, and it'll tell you how to choose these M's in a way that's efficient. All right. Okay, so let me just okay, so what we're going to do is we're going to look at a min hash on a set S. Okay, and we're going to use K of these these are going to be, let me write this out just so it's clear, that these are going to be K of these random hash functions. Okay, and these are going to be like the hash functions that you're using on your homework. They're going to be like the ones that we discussed in the in the second lecture. What they're going to do, so it's going to be H1, H2, up to HK. And so each of these HI is going to go from some element in my universe to something, let's say, up to some domain of size n, and in general you probably want n to be larger than the size of the universe. You can, if you make it a little bit smaller, it's probably actually going to be fine. You may have some collisions with this birthday paradox, but we can discuss that a bit later. Those shouldn't really affect the answer too much. But you probably want to go to some domain larger than this. So you can make this a power of 2 if you want to. You can make this a large prime, whatever's easy. Okay, so now for so we're going to have this algorithm for each element. Let's call this small s in my set. So I'm going to go for each I and k. So for each of my hash functions, so these are looping over the elements. These are looping over the hash functions. Okay, then I'm going to say, I'm also going to say that I'm going to keep track of these values here. So I'm going to have these values M1, M2, up to MK, which are going to be my output values, and each of these I will start so that initialize, so mi is equal to infinity, or some very large value. Maybe it's this n plus 1, right? So infinity is n plus 1 now. And so now, if my output of my hash function on S is less than my value mi, then I'm setting mi equal to this value. Okay, and yeah, so that's the whole algorithm. So let's go through this and make sure we understand how this works. So this is the whole algorithm. So you loop through every element. For each element, you're going to essentially, for each element, and then for each hash function. So you're doing this for k different permutations. So for each one of the permutations, you want to hash it to some value between 0 and n, which is really large. And this is going to kind of serve as a permutation. That's saying I'm taking this element and I'm saying where is it going to go into this permutation. And this hash function is not going to be perfect, right? It's not exactly a permutation, which is giving me a true ordering, a reordering of these elements, but it's working well enough. And you can show that the same proof that we went through before is gonna work the same way as if we were doing these permutations. So I'm gonna hash these things, and if the hash function is less than m, then I'm assigning this the value. Right, so now the value is the element of this hash function. I can assign it to, before I gave it a value, I set this was equal to, I said this was equal to s inside of the example I gave before, but I can just as soon give it a value which is the order it's been permuted into. This will serve the same property of whether these two things intersect. Right, so all I needed was the property is the probability that they intersect is going to be this x over x plus y property, which is the number of things that are common to both sets over the union of both sets, right? And so each is going to intersect with probability, 1 over the union, or it's going to intersect with two things that are not the same are going to intersect with probably 1 over n. Which is, if n is big enough, is going to be really small, and that's going to be is going to be negligible in my estimate, in my error. And there are ways you can take care of these a bit more by going through that analysis a little bit more carefully. But it's a pretty simple algorithm. You can make one pass over the data, and for each element, you apply to each hash function once, right? So if assuming the hash function can be done in constant time, then the runtime of this, so what is the runtime of this algorithm going to be?
The number of elements in S times k.
Yeah, so it's going to be the size of the set times k, right? So it's going to be one pass over the set, and for each thing I just need to hash it these k times. And so if k is 1,000, you can do this fairly quickly. But the thing is, it gives you this representation, which will be able to find similarities very quickly, and we'll talk about that next time. Right. So before saying anything more about that, let me just pose this question, which we'll answer in next lecture. And then we can come back and answer questions about this. But I want to show why this is interesting to do. So say you have, so let's think of two ways of representing these documents. One way is to map it to these sets, and then you can go into these min-hash Minhash vectors, right? So this was one way of doing it. We could have also gone straight to these vectors using the bag of words. And these vectors will be slightly different than these. These Minhash vectors will have a very nice property where the number of elements which are exactly the same, the fraction of those is going to estimate the Jacquard similarity. These vectors are going to do something different, but we can handle, there'll be another way to handle these. Another simpler way is just to say, is go to a single number. So a number in the reals, or even an integer. So let's say that this is equal to just the number of words in the document, something kind of stupid. Right? Each of these choices, I had some choice in the modeling. Let's say I made a really simple, stupid choice, but now I have a single, each document is a single number. Okay, so now I want to find all the similar documents, all the documents which are within a distance of 10 from each other. For some 10, if I look at this representation. Right, so I have a whole set of documents. I have all my emails, right? Or I have all the homeworks you've turned in. Or I have all the web pages on the internet. And I want to find all the ones which are similar enough. They're within a distance 10. And I use this representation. So what's the right way to do that? So this should be easy. And then want to think about how it might be trickier to do that for these other representations. So how would you, but this one should be easy. You have a bunch of numbers, right? So I have all these documents, D1, D2, D3, up to Dn. And I've mapped each of them into a number. This was 72 words. This was 103 words. This was 400 words. And this was 80 words. And I want to find all the ones which are within a distance 10. How would I do that for all pairs?
You just count how many words there are and just see if there's within 10 of each other?
Yeah, but so I can generate these numbers, right? I can count these words. But then how do I find the pairs which are similar? How do I find those similar pairs? Yeah.
Is it the mean standard deviation for the document, for the document class?
Well, no, I have it. I don't care about anything else but the number of words. So I just have these numbers. I want to find all numbers which are similar. Right?
Sort the differences.
Yeah, so I can sort. So if I sort these numbers, then I'm going to output, I'll have a sorting, and let's say that, there's a document that had 1 word in it, then it had 7 words in it, and I got up and it had 72 words in it, then it had 80 words in it, 103, and so forth. And I knew that this corresponded with D1, this corresponded with Dn, and then I can do something where I kind of scan over here. So let's say and I say, these are next to each other and they're within 10, so these are similar. Once I have them sorted, I can kind of scan over and pick out all the ones which are similar. So I can do that pretty easily once they're in sorted order. Okay, but this is a really simple representation. It's a single value. How would I do that if I had these multiple different these vectors? Yeah.
Bound volume hierarchies.
So bounded volume hierarchies. Hierarchies. Okay. So so those are some big words that probably most of you probably don't mean what this know what this combination means. It's this is going to work in maybe when the size of your vectors gets up to maybe 4 or 5. It works really well for 2 or 3, and afterwards it can sometimes work. This is where you take kind of like a high dimensional space, and you kind of say, I'm going to divide up this space into parts. And say some of the points are over here, and some are up here, and if they're in the same space, then they might be similar to each other. At a high level, we'll actually talk about this a little bit later. So there are ways to kind of make this work. but they work under certain conditions. We can kind of make them work, and we'll talk about those actually next week. Yeah.
So what he's talking about, is that similar to like a multi-dimensional tree?
Yeah. So there are words. So there are the things like a KD tree, right, which is a type, and there's also things like an R tree, which is used a lot in databases. This works up to, again, a handful of dimensions. There's something called a range tree, which has really nice theoretical properties in 2D, and there's something called a quad tree, which is in 2D, but you can generalize that to higher dimensions. This also has really nice theoretical properties, but the KD tree tends to work well, and we'll talk about this. But this is not the technique I'm going to use. These kind of they don't scale that well with dimensions because high dimensional space is really weird. And I'll spend time kind of explaining why it's strange. And you can draw pictures in 2D and things seem to work. In high D, these things kind of break down. And you're going to want to use these other techniques that these locality-sensitive hashing. So what you're going to do is you're going to kind of hash these things in a way that preserves locality again. So after I've hashed them into these vectors, I'm going to hash them one more time. And it's still going to work.
Is that using things like Hilbert curves or Z-orbit curves?
There are ways to do that, but those, again, only tend to work in a few dimensions. But in few dimensions, those work really well. Yeah.
Can we do least squares or a linear program of some kind?
A least squares or linear program. We'll talk about ways of doing dimensionality reduction. So you find the lower dimensional subspace they all fit in, and that'll kind of be like least squares. But linear program is solving a single objective. We're trying to find a set of similar things. We're trying to discover this instead of solve a single objective.
Like something like cross-region method, where we kind of cross one region or certain values and then try
So I couldn't quite hear you. So maybe you can ask me a little bit after class. But so this line to think about. We're gonna see a way how to do this. So on Wednesday. So kind of if you want to challenge yourself, think about how you would do this. So.
Can I ask you a few questions?
Yeah.
So this K was different from the one. What's the difference? Because
I screwed up a 2 someplace.
So this is the right one? Because I think
I messed it up here. It should be
because it's actually repeated in multiple. I think I saw.
I probably copied. I just copied it over probably.
So this needs to be fixed. I mean, this is.
Yeah.
Because that one made more